Yes,
Yes,
that's perfect.
Fantastic. Very good. Then I'll start speaking. I think I will be speaking maybe 35 minutes, leaving 5 minutes for the questions or something like this. And I lost 5 minutes because of the introduction of the David. So it is a joint work with Azamov, McDonald and Zanin. And that joint work was just published very well last month by the Communications in Mathematical Physics. So that's the reference where it appeared. And the talk is about connection between, which I would rate as a surprising connection between two topics. One is the density of states in mathematical physics, which attracted, maybe thousands and thousands of publications of including top-class mathematical physicists and also proper physicists, real physicists. And the topic which my main interest in mathematics, which relates to non-commutative geometry of Alan Kohn and its connections with mathematical physics, and which we seems to be discovered this unexpected connection. So that's Dixmier trace formula. It is the Alan Kohn's invention, and I will explain what it is about. So, and how it actually relates to the topic of the conference, which called the non-commutative analysis, right? So there are the words non-commutative analysis in the topic of the conference. And this Dixmier trace formula due to Kohn, it's actually the fundament for quantized calculus of Alan Kohn, which we also can say the non-commutative analysis of Alan Kohn, if you wish. So, but I will start with the basic stuff which comes from the mathematical physics, and I will explain what is the density of states, what is its interest, and what it is all about. So, notations. I will be working in the D cube. So I'm working, this D cube is taken in the D-dimensional Euclidean space. And this D cube, I denoted this omega L. So L is the length, 2L is the side length of the cube. I will be working with a classical Laplacian on the cube, with a Dirichlet Laplacian on the cube. And therefore, its Laplace operate on functions vanishing on the boundary. And as such, since the cube is finite volume, the resolvent of my Laplacian is compact. So it's much easier object than, say, the Dirichlet Laplacian on the Euclidean space. I will also work, of course, with a Schrodinger operator, and to this end I need function v, that let it be, at the moment, let it be, say, a bounded function on omega L, and mv is this, will play a role of perturbation, so it is a multiplier by this function v. So it's bounded functions on this d-dimensional space. So Schrodinger operator is my Laplacian delta L plus mv. Since we only consider bounded v and h is self-adjoint with a domain equal to this delta L, then h is a relatively compact perturbation of my Dirichlet Laplacian. And therefore, this is of course a theorem, and therefore the spectrum of H is still discrete and consists of the eigenvalues of finite multiplicity. In the language of spectral theory, H has no essential spectrum. This again makes it much easier to study if to compare, say, with the classical Schrodinger operator on the Euclidean space. So that let's again remember those notations which I will be using throughout the talk. So H is this Schrodinger operator, Laplacian plus multiplication operator MV. It's completely classical setting. So what will happen if I will move from bounded domains to the unbounded domains? If I again take delta classical Laplace operator on L2RD, then it is a self-adjoint operator, but it now has the spectrum minus infinity 0 and has no eigenvalues. So the spectrum becomes essential spectrum. And so I still would like to consider the Hamiltonian H minus delta plus MV. V is now not necessarily on the cube, but on the whole space. Still a bounded function, so let's avoid any of those difficulties. Then let's ask the question, what does the spectrum of H look like? As I said, it's a very, very classical question to which enormous number of people contributed. And a lot of the classical spectral theories exactly studies the spectrum of those Hamiltonians. Well, that's the couple of those pictures and a couple of the reference. So suppose V is periodic, then the spectrum of the periodic Schrodinger operator is purely absolutely continuous and consists of the union of bands. That's part of the celebrated Floquet theory, about which I know almost nothing except of this fact. And another also very famous theory, Anderson localization theory, which is done for the random potentials, says that the spectrum of the random Schrodinger operator has almost surely a pure point bottom part. That's the picture. As I said, both of those theories are very well established. There's huge number of results here. It's completely impossible even to list. So these are the things which are interesting to us. So that you see, something happens with the spectrum under the certain conditions on V, something happens with the spectrum of the Hamiltonian, and we would like to understand this phenomenon. Now, how physicists actually come to study the spectrum of Hamiltonian. So let's again return to the situation when my Schrodinger operator is on the cube, omega L. At some stage I will start vary this side length L, but at the moment L is fixed. So we know that H has only eigenvalues of finite multiplicity here, and so we can introduce the counting function. So I took an arbitrary real number T, and then I count the number of eigenvalues which are less or equal than T. Equivalently, you can think that NT of H is the dimension of the span of eigenfunctions with the corresponding eigenvalue less or equal than T. H is lower bounded, has no essential spectrum, so I know that this spectral counting function is always finite. And so a lot of our work is done with this for the studies of these counting functions depending on the multiplier MV. Well, what will happen if I will replace omega L with RD? Well, in some situation, it is known that these spectral counting functions remain finite for certain values of T less or equal than the 0 under certain conditions of V. These are so-called famous Zwickel-Lie-Brasenblum estimates. However, generally speaking, the spectral counting function doesn't make any sense for the Schrodinger operator on RD since the spectrum can be continuous. How to replace this spectral counting functions. And the physicists do it as follows. So idea comes from physics. So we look at this minus LL cube, and we say that we restrict, I take the word restrict in the brackets, so in the quotation marks, because it's not a proper restriction. The H is not restricted. I'm simply looking at the HL, which is given like minus delta L plus MV. That's the physical idea of the restriction of the classical Schrodinger on the big space to the small space. Well, as soon as you are now in this discrete spectrum situation, and and HL has only the discrete spectrum, we can count NTHL, so it's a well-defined number. Let us now assume for a second that the limit of this NTHL divided by the 2L to the power D, which is the volume of my cube, exists. Well, when the physicists started this thing about close to 100 years ago, they simply postulated, yeah, that simply exists. So let's consider this limit exists. And if this limit exists, then it can be shown that this limit, in fact, defines the measure, which I will denote nu of h minus infinity t on this interval minus infinity t. And precisely this measure is called the density of states of the Schrodinger operator H. As I write here on the slide, optimistically, this limit exists and indeed defines a measure. Of course, this will be a number of theorems to verify whether this happens. What are the conditions on V under which it happens? But we know that, say, in this, say, Anderson localization techniques and other theories, this Cloquet theory, that it does indeed happen. There are plenty of analytical issues with this density of states measure. So, does the limit really exist and does it define a measure? Answer, not always, but sometimes it does. If it exists, what's the support of this measure? Answer, the essential spectrum of my Schrodinger operator, my Hamiltonian. Does it depend on the choice of the boundary conditions for HL? You see, I chose the cube and I was talking about Dirichlet Laplacians. The answer is no. Whatever periodic boundary condition you choose on minus LL, it will result in the same density of states measure. That actually shows that we are dealing with a very fundamental thing here in physics. So it's really something deep and really expresses the properties of the Hamiltonians. It also remains the same if you will change boundary conditions. You went from Dirichlet to Neumann, or periodic boundary conditions. Still, if this limit exists, you will recover exactly always the same measure. It's kind of, all of that is simply shows that it's actually an interesting object to study, an important object. Well, I'll give it only one example, and it's indeed will be a very simple computation to perform, which I will not perform, but I will simply show that if I have a free Hamiltonian, what does it mean, free Hamiltonian? It means that the function V, the multiplication operator which I use to perturb the Laplace operator, is 0. Then in this case, the computation is supposed to be very simple, and we could recover our density of states measure, which is given by this formula. Have a look at this formula. It's indeed so volume SD. This is just the volume of the unit sphere in d-dimensional. Euclidean space. And you see, we are having a classical Lebesgue measure dt with a density maximum t, comma 0 divided by 2 minus 1. This computation can be performed by any student. So there is nothing here basically to compute it. It's straightforward computation. So in these trivial cases, we see that it exists. And I will demonstrate you now that this will be linked with the very interesting stuff in the non-commutative geometry of Alan Kohn. So now we will go to something completely different. So I will take you now to from this very short excursion to physics of solids, mainly Schrodinger operator for the solids. But to operator theory and non-commutative analysis. So firstly, let me recall the definition of the singular value sequences for compact operators. It's very close linked with the eigenvalue sequence, and say if my operator T, compact operator T, is non-negative, then what I'm singular value sequence, eigenvalue sequence simply coincide. So what is the kth singular value of this operator T? It's the infimum when I approximate T with a rank, finite rank operator R, whose rank must be less or equal than K. So for example, if K is 0, then infimum of T minus 0, right? So what is this? This is simply the operator norm of the operator of compact operator T. So 0th singular number, it's simply the operator norm. Then you take the, say, the rank 1 operator and approximate T as best you can, and then it will be the first singular value, and so on. We approximate it, and then we get a sequence of eigenvalues, which we always arrange in the non-increasing order, counting the multiplicities. Since my T is compact, then this sequence goes to 0. We say that a compact operator T is weak trace class operator, and we write it like T belongs to this script L1 infinity. So this is weak trace class operator, provided that my singular value sequence is like, behaves like 1 over K. So Kth singular number is approximately 1 over K. Or equivalently, the quasi-norm, 1 infinity quasi-norm given by the formula 1 plus K, mu K plus T, less than infinity. So my singular value sequence should decrease like the harmonic sequence 1 over K. This is a very, very fundamental object in the non-commutative analysis. It is principal ideal with this singular, defined by this singular value sequence, and it plays an important role in the non-commutative geometry. So the role is the following. It's in Alan Kohn language, the weak ideal L1 infinity, it is the non-commutative infinitesimals of order 1. And those non-commutative infinitesimals of order 1 are important because they have non-trivial singular traces. So singular trace, it is a usual trace, so it is positive unitarily invariant functional, which vanishes on all finite rank operators. And the most famous example of such traces is Dixmier traces, as given by the so-called Dixmier traces. You remember that when I'm working on the weak L1 ideal, then my singular values mu K of T behaves like 1 on K. So if I will take the sum of those capital N number, 1 plus 1/2 plus 1/3 plus 1 on n, it is just a log of capital N. So log of capital N divided by log of capital N, it's a bounded number. It's a bounded sequence. So I've got a bounded sequence depending on n. Well, I apply some special extended limit, and the number that's a result of Dixmier 1966. It happens that this strange approach generates indeed a trace, unitarily invariant positive functional on L1 infinity, which vanishes on all finite rank operators. A property of those Dixmier traces is that Dixmier thought that exactly that fact that it vanishes on all finite rank operators make them useless. His student, Dixmier's student, Alan Kohn, realized that it is exactly that property which makes them extraordinarily useful. And he made those Dixmier traces or singular traces on weak ideal the most important computational tool in his quantized calculus, which underlies the whole building of non-commutative geometry. Alan Kohn proved the following formula, that if f is a compactly supported smooth function and mf on Rd, so everything happens now on Rd, and if I will look at the product mf times inverse resolvent of a Laplacian, it's in fact already non-trivial to say why actually this operator will fall into the L1 infinity. So the fact that the operator standing on the left-hand side belongs to the L1 infinity is a very non-trivial result. But it does belong, and so I could compute this Dixmier trace on that. So I apply this Dixmier trace on the left-hand side, and lo and behold, what will happen? And this is one of the most fundamental formulae in the Alan Kohn quantized calculus. Lo and behold, I recover Lebesgue integral of f. It's a very, very strange formula when you think about that. So of course, on the left-hand side, we link the two most important operators in analysis of multiplication and differentiation. Thanks to certain Zwickel type estimates from mathematical physics, it happens that this operator belongs to the Zwickel one. And therefore, we could compute a very strange animal, trace omega, so Dixmier trace, singular trace on that product. And by a complete miracle, we recover the Lebesgue integral of f. It's a very, very interesting stuff. At least for me, it was for many, many years. It's actually defined my work in the non-commutative geometry that's exactly interest to that fundamental formula. And so I will now demonstrate to you that there are direct link between this formula of Alan Kohn and the density of states. Now restrict our attention, so f was an arbitrary C-infinity compactly supported function. I will now take it such even more special class of function, radial function. So it's a function which depends only at the distance from the zero. So f of t is another function g of absolute value of t squared. So my function f takes now only one value on every sphere, depending on the radius of the sphere. Well, the first line in the display, which is in front of you, is still the same formula. I just substitute g of t squared instead of f of t, and then I simply compute this integral. Make a substitution, so because now g of t is a function of one variable, so I make a substitution, use the spherical coordinates, and I arrive to the formula integral from 0 to infinity g of r, and that's these coefficients come from this substitution formula. Now I will switch to the Fourier side. Why could I do that? Fourier transform is a unitary transform. Trace omega is a trace. So trace is a unitary invariant functional. And so I apply on the left-hand side of my first display this Fourier transform formula. And what will I get? Well, instead of m of f, it will be now g of minus delta. It should be nabla, but remember, my g is a function which depends on t squared, so it's g of minus delta. And of course, my Laplacian after the taking of Fourier transform becomes simply the multiplication, square of the multiplication operator, 1 plus mx d squared. Now have a look what is actually happening here. I replace the measure on the right-hand side of the formula with a nu, with d nu of r, taking the density into this measure. And now look at what happened. On the right-hand side, by some miracle, I actually have the density of states for the free Hamiltonian from which I started. I just, on the span of 3 or 4 or 5 minutes, I actually demonstrated to you that I could arrive that there are direct connection between this cons trace formula on the left-hand side and the density of states measure. That was the first observation which we did and which underlies our future work. So now I am coming to the main idea. So we saw that in the free Hamiltonian, it's actually happening. There are connections. Let's now take the bona fide Hamiltonian. So let's replace Laplacian with the Hamiltonian H. Well, having done that, we would like to see what will happen. And it happens after some work, of course, which involves various techniques from the theory of non-commutative analysis, Dixmier traces, and so on and so forth. We indeed proved that in the case when the density of states measure exists on the right-hand side of this display, that it's actually coincides with the measure which can be obtained through this singular value functional given by this trace of omega. So the formula, the main result sounds as follows. If the density of states measure nu of h exists, then it is given by the formula where on the left-hand side, you see this trace omega. It's still a singular functional f of h. But have a look here. Why do I say that we use the Rees representation theorem? F is now an arbitrary function. On the left-hand side, you have a continuous functional. Yeah, it's given through this singular trace omega, but it's still a continuous functional. And therefore, I can actually say that by the Rees representation theorem, it gives me the measure. And this measure, have a look now on the right-hand side, this measure, which I obtained through this application of this constraint theorem, is exactly nu of h, density of states measure. This is, somehow was very, very surprising to us. And we discovered that using our technique and this result, we can also show some new properties of the density of states measure. So it simplifies certain proofs of the density of states significantly. For example, it shows the insensitivity to the localized perturbations, makes certain computations much, much easier. So for positively homogeneous functions, we also discovered the new formula for the density of states measure. And what else I wanted to say? And and the last slide will be like lies and omissions in this talk. Well, I told you that we were doing this for the cubes for simplicity. In fact, we were working for the balls, but as I said, the results, fortunately, the same. Whatever approximations for the classical Laplace operator on RD you choose, whether you choose the Laplacians on the cubes or on the balls, the result the same. The result the same. And the second, well, not lie or omission, was that we did not really use the physicist's definition of density of states, with which I'm shown. We used the equivalent definition of density of states, taken from the Barry Simon's book and from his papers, which is given by this formula, and it is not immediate. So this formula which I write here is of course not immediate. However, in the most important cases, it is equivalent to the physicist's definition. That's sort of, so it's important to be honest. So, and that was my last slide. Thank you very much. And I think I made it in 35 minutes. Right.
Oh, so yeah, you were perfectly
in 30, actually in 30 minutes. So now.
Thank you very much for this very interesting talk. Yes, are there any questions? Please come forward.
I have one question for Professor Sukochev. Yes, I remember one very beautiful theorem from non-commutative geometry, in the sense of Alan Kohns, is that what agree with the Dixmier trace. Then I don't know if for this kind of Schrodinger operators, in the case of unbounded domains, we have a similar theorem. I mean, 1 minus the Laplacian with power minus d over 2 is a classical differential operator. Then
yes, correct. Go on. Yes, exactly. That's a part of this. That's where it comes from. So Alan's Kohns trace theorem was stated for the pseudo-differential operators of order minus d. D is the dimension on the manifold at which it is. So this formula, so what is written here, or say when I started, have a look here, MF 1 minus delta 2 minus d on 2 is a very special case of those pseudo-differential operators of order minus d. So the Kohns trace theorem is given for this exactly for the pseudo-differential operator. However, when you look at those operators of that special form, like this one here, then when you specialize this Kohns trace theorem, that what you get, that's what is called Kohns integration formula.
Wow.
So and that's exactly what is written here. This Kohns integration formula allows to recover the Lebesgue measure for these operators. But yeah, you're absolutely correct. The original setting of Kohns trace theorem for the pseudo-differential of order minus d.
Thank you very much.
And as soon as we specialize it to this MF times Laplacian to the power minus d on 2, we get that formula. So
yes,
integration formula. Yes,
it's a very beautiful formula. Thank you.
Oh, that's fantastic formula.
Yes,
one of the most remarkable which I ever seen in my life in analysis.
Thank you.
It's.
So, are there any other questions?
Yes, can I ask?
Yes, please.
While you are in the same page, why do you prefer mod t square to mod t? Because the radius is mod t. So why do you prefer mod t square?
Are you talking about this formula here?
Yes.
Oh no, this is only for demonstration purposes.
Okay.
So I started with a function f of t. I wanted to demonstrate how I can massage Kahn's formula on the left-hand side in order to obtain the density of states formula on the right-hand side. To this end, I took a special example of functions f, which depends only on the radius. So, and with this trick, computing the right-hand side, I showed to you that what happens here, this measure is exactly density of states measure for the free Hamiltonian. It was done with only one purpose, to show this connection. And that's actually how we actually encountered how we made this discovery. We simply computed. So look at this formula, played the game. Let's have a look what happens when happens. And then it was realized, hey, lo and behold, that's actually density of states for the free Hamiltonian. That was the beginning. Then we asked the question, can we actually prove it in full generality? Will it happen for an arbitrary Hamiltonian, provided that the density of states measure exists? And the answer is yes.
And on slide 12.
Say it again.
Slide 12. 2 slides before this.
Two slides before this. Yeah.
Yes.
Yeah.
What is this star in line 4?
This is, so L infinity of n is the algebra or a Banach space of all bounded sequences, uniformly bounded sequences with a norm given by the uniform bound. The star is that it is a continuous linear functional on this L infinity of n. And this is so-called extended limit. In other words, that this extended limit coincides with the classical limit on all convergent sequences. That such limit exists. That's the kind of the, you probably heard this words like Banach limit or something like that. So this is a Banach limit basically.
Fine, thank you. Wonderful talk. Commuting with audience, even though non-commutative talk.
Thank you. Are there any other questions?
May I ask please?
Yes, please go ahead.
Yes, there are some integral formula other setting than Euclidean case RD.
Should I go where to this formula?
Yes, for example, for this.
To which slide?
What happens if you change, if you replace Euclidean case with another manifold, for example?
This is an open question. You pinpointed exactly the theme of research we are doing right now. Yeah, you're absolutely correct. It will be very interesting to study density of states on the manifold. Density of states, an enormous subject, absolutely enormous. I know very little. So people look, first of all, not only on RD, they look at the Schrodinger operator on ZD. You know, this is also the discrete Laplacians.
Discrete Laplacian, yeah.
This is, then they look also on the manifolds, the Laplacians, on Laplace-Beltrami operators on the manifolds. What happens there? But this is the first paper which, as I said, was just written very late last year, just published. But yeah, we're looking at the discrete Laplacians on the ZD. And we are looking also what will happen on the manifolds, on the general Riemannian manifolds, for which we know that the density of states exists, yes.
So I guess this also raises some very interesting questions for the Michaels group here in Ghent. I mean, many of us are working on Capekli groups, nilpotently groups, etc.
That's exactly the reason why I accepted accepted the invitation to speak at this conference. It's a pity that Michael is not here. So
yes,
my greetings, please pass on.
Yes, I will forward them. Thank you.
Thank you.
May I ask you a short question before we move on to Professor Rösler's talk? Can you maybe just briefly give us some intuitive insight to why this density of states measure is so insensitive to the boundary conditions of this restricted?
No. It actually, once again, we do not know many, how to say, there are special situations when this density of states exists. We simply looked at those situations when we know how to compute, and we proved that it is insensitive to the boundary conditions. The full theory does not exist. I'm simply speaking from the experience that what we have and verifying by hand. So what will happen if you will play with the balls and with the cubes or with some other figures? By the way, since we are speaking, you are in Ghent, and Ghent is in Belgium.
Yes.
I must say that if you will look at our paper, there is a reference to the absolutely fundamental paper in this area due to Bourgain, to late Bourgain, which, so this density of states and the property of that measure actually attracted his attention. And in our paper, there is a reference to Bourgain's paper in co-authorships. Somebody, I don't remember the name, but I remember that it was Inventiones Mathematicae paper, which is very widely cited in this area. So also was kind of so this topic attracted also attention of the top class mathematicians like Bourgain to studying the properties of density of states measure.
Well, thank you very much. Thanks once more for this very interesting talk, Professor Sukochev.
Thank you for having me.
And then, okay, thank you. So then it's my pleasure